webcast talks about uniform circular motion. Uniform circular motion means something that moves in a circular path at a constant speed. So for example, a toy car going around a circular racetrack, as shown in the picture here. So even though the speed of this car is constant, the velocity is continually changing. And the reason is because the car's direction is always changing. Three different positions are shown in this picture, and you can see the velocity vector is always moving straight ahead of the car, but the direction of that velocity vector keeps changing because the car has to keep changing directions as it goes around the circle. Remember that velocity is a vector, and so it has two types of information associated with it, the speed and also the direction. And so even though the speed may stay constant, if the direction is changing, then the car is accelerating because its velocity is changing. This type of acceleration, which is due to something moving in a circle, is called radial acceleration, A with a subscript of R. One of the important characteristics of something that's moving in a circle is how much time it takes for the object to make one full trip around that circular path. This time to make one full revolution is called the period, and the symbol for period is an uppercase T. So if you have something that's moving in a circle at a constant speed, the period is equal to 2 pi r divided by v. 2 pi r is referring to the circumference of the circle, so 2 times pi times the radius. The v is the tangential speed, just the speed that we've always talked about in meters per second. So the period is equal to the circumference, 2 pi r, divided by the speed, v. The standard units for period are seconds. So period is telling you how many seconds it takes to make one full trip around the circle. So for example, there's a toy train here going around a circular track at a constant speed of 8 meters per second. The radius of the track is 0.6 meters, and we'd like to find the period of the train, which means how much time does it take for this train to make one full trip around the circular track. And so we could say that the period is 2 pi r divided by v, and we would get 0.471 seconds. Now we could also modify that same equation and isolate the v, or the tangential speed, instead of the period. So if we know the radius of the circular track and the period, which means the time that it takes to make one full trip around that circle, we could find the tangential speed as 2 pi r divided by the period t. So if you look at the example of the record disc at the bottom of this slide, think about a record. It is a solid object, and so every point on that record revolves around the circle at the same rate. And so each point is making a revolution around the circle in the same period t. But when you compare the tangential speeds, you'll find that something that's toward the outer edge of the record will have to move faster than something that's closer to the center of the record. And that is because the objects that are toward the outer edge have a larger circumference that they have to move through in that period t. And so they have to go faster to move all the way around in that amount of time. There's also a common way of describing motion in a circle, which is a rotational speed. which gives the number of revolutions per unit of time. And typically, in our common language, we'll talk in terms of a unit of RPM, which means revolutions per minute. Whenever you encounter a description of rotational motion in RPM, you need to immediately convert that to period. And the way that we need to do that is to first of all convert the minutes to seconds by dividing the RPM value by 60. And then you need to take the inverse, in other words, 1 divided by that number, because a period is how many seconds it takes to make a revolution. RPM is how many revolutions can be made in a certain amount of time. So here's an example of that. So here is a bug riding on the edge of an 8 centimeter disc that's rotating at a rotational speed of 45 RPM. And so the first thing we do is convert that 45 RPM into period, which will tell us the number of seconds it takes the bug to make a full revolution. So we convert 45 revs per minute to 0.75 revs per second, and then we take the inverse. And that says that it will take 1.3 seconds to make a full revolution. So the period T is 1.3 seconds. Then we can find the tangential speed as the circumference divided by the period. So 2 pi times the radius, and then divided by the 1.3 seconds, which is the period. So this bug on the edge of the disk is moving at a tangential or speed of 0.38 meters per second. What if the bug moved closer to a point that's only 4 centimeters, so about halfway between the center and the edge? And let's find the tangential speed there. The period is the same. It's still moving making a full revolution in 1.3 seconds, but now the radius is smaller, and so the tangential speed is smaller. So as the bug moves toward the center of the disk, its tangential speed approaches 0. It gets smaller and smaller. We can find the radial acceleration by taking the square of that tangential speed and dividing it by the radius of the path. In uniform circular motion, this radial acceleration vector always points toward the center of the circle. And in uniform circular motion, which means moving around a circular path at a constant speed, this radial acceleration has a constant magnitude. So for the toy car, or the toy train again, moving at a circular path at a constant speed of 8 meters per second, the radius of the track is 0.6 meters, and so we could find the radial acceleration. It would be the tangential speed squared divided by the radius of the path. And that acceleration always points toward the center of the track. So think about something that's moving in a circle. For example, this man is holding his backpack and swinging it in a circular path. What kind of force would he have to exert to make that backpack move in a circle? Whenever something moves in a circle, there has to be a force that causes the object to move along that path. We know that if there were no force, the object would just move in a straight line path. We know that from Newton's first law of motion, which says that whenever an object moves at a constant velocity, that means a constant speed in a straight line. So there has to be a net force that is non-zero that makes an object move in a circle. and that force is called a centripetal force. That word centripetal means center seeking, so the centripetal force points toward the center of the circle. So that centripetal force is equal to the product of the mass of the object and its radial acceleration. Any type of force can be a centripetal force as long as it is serving to make an object move in a circular path. So, for example, with the boy swinging his backpack, that would be a tension force that is causing the backpack to move, to keep changing direction so that it is always moving in a circle. It keeps moving back toward the center. The moon moves in a circular orbit around the Earth because of the gravitational force that the Earth exerts on the moon. When a car goes around a sharp circular curve, it is a friction force, or perhaps a normal force if the road is banked, that keeps the car from sliding off the road. So this bike rider is going around a circular track at a fast speed of 25 meters per second. And if we wanted to know the centripetal force on the rider and his bike, we would have to find his centripetal or his radial acceleration and then multiply it by his mass.